it told me that recording started now. So, all right, let's talk about organic chemistry. Uh, all right. So this week, or maybe more than a week or so, you've been learning about chapter 22, which is aldol condensations. And if I were to organize this course, I would say that this is like one of the biggest parts of the course. This is really one of the most substantial things you learn. This is like really a new class of reactions that you just haven't seen before. So, to start things off, uh, maybe I just wanted to put things into perspective a little bit. Okay. So, in Orgo 1, you learn that if you have a CH bond where the C is sp3 hybridized, then the pKa of it is 45. Okay. In other words, you're never going to see this thing dissociated. It truly won't happen. Right. And then you learned a whole bunch of stuff about like inductive effect and like a whole bunch of other things, right? And you learned how to classify the acidity of hydrogens and so on. Okay. And in this chapter, what you've learned is that if you have a hydrogen over here, then the pKa of this is 20, which is like a huge, huge reduction, like a massive increase in acidity. This is such a major difference. Like, just for perspective, you learn that when you have C triple bond C and then an H, this was around 25. Okay? And think about everything you could have done with this. This was like huge back in the day. Okay? So now here you are, and you could take this hydrogen off even easier. Okay? So, like, this was the most use at one point in time, this was the most useful reactant that you knew. And now here you are, and you've got something that works even better. So as you can imagine, this is going to be like even more powerful and going to let you do way more stuff. Okay? So also you have things like if you have an ester and then a hydrogen that's next to it, then this is around 25 as well. So also really useful. You could do a whole bunch of stuff with that. All right. And now let's say that you put two carbonyls there, two ketones, and you have this hydrogen. The pKa of this thing is like 9 to 10. Okay? This is honest to God acidic. Like, you could put this thing in water and you could expect that a lot of it will be dissociated, which is crazy. Okay? Uh, for reference, other things with pKa of 9 to 10 are like if you have like uh, phenol, that's an ugly phenol. Okay. Uh, if you have your phenol is like 9.9 or HCN, which like you would definitely call an acid is around 9.5. Okay. So other things that you would definitely call acidic, this falls in that category as well. Okay. So this is an easy thing to work with. It's super powerful because like you could do a whole bunch of reactions with this stuff. So what you're learning in this chapter is basically how to take advantage of this acidity and to do like really powerful and really classical reactions with it. Okay. So this is like back in the day, this is how a lot of reactions would be done, especially for making carbon-carbon bonds, because this is what this method is the most powerful for. Okay. So what you can do is take any of these things and then use, or you could have like the ester uh, or whatever, or like this thing, and you can use a very strong base. And in this section, you learn about a base that's LDA, which is like the base that you want to be using for this stuff. So you could take these, and then from there, you can make an enolate. which you've seen a whole bunch of before, and this is the powerful thing that you can react with. Okay. And it's probably worth mentioning there's like an extra alternative, which is that you could take something that is like a ketone and then give it a secondary amine, and then that'll give you what is here called an enamine, which looks like this. So up here we had an enolate, and down here we have an enamine, and this will also react pretty similarly because all of the electron density is around here. Okay, so it's good to mention that all of the electron density tends to be down here. Or for this nitrogen, all of the electron density tends to be down here. Okay? Which means that this is a good nucleophile. We can really do reactions with this in the same way that you could do reactions with like I don't know, whatever your favorite nucleophile is, right? This can displace halides, it can displace tosylates, it can get rid of a whole bunch of stuff. So that's what makes this really useful. All right. But not only can it like displace things, you can also use it to actually since it's a nucleophile, you can also use it on other carbonyls. Okay? So let's say that we have this enolate and we add it to, I don't know, another one of these, right? Then the electrons will attack from here like a regular nucleophile and push this up to there. So this will go and make a bond that goes there. Okay? And from there, if you want, then you could take this O minus and you can give it to some water. Right? And there you go. Like, you've made a totally new sort of compound which has an alcohol that is, maybe let me pick a new color for this. So here we have the ketone, and then here's the alpha carbon, and then we have the beta carbon. So now we have an alcohol that's beta to the carbonyl, right? And maybe this isn't like super revolutionary to you. You might think like, all right, whatever. That's kind of neat. But the position that things are relative to ketones will wind up mattering a lot. Okay. So in this case, we did a basic addition, and let's say that we just kept it in the base and we just heated it a whole bunch more. Well, from there, you know what you can do, right? There's a hydrogen hanging off here. Okay? And you could do E2. Okay? And from there, you can turn this into a double bond. Which is, I mean, that's also useful, right? It's the same reaction. You already had base in the solution, so now all you're doing is just heating it a whole bunch more and you've gotten a double bond out of it, right? So this sort of structure is this is like a common structure to see. Right? And when you have this sort of like ketone next to a double bond, then, well, you can work backwards because you know what it must have come from, right? There must have been an alcohol on the carbon that is farther away from the ketone. And from there, you know which ketone attacked which one, so you can work backwards. Okay? a very common type of problem that you'll be working with when you're doing like all of these aldol condensation reactions is retrosynthetic analysis. Most of the problems that we have to do today on the uh, for the workshop are retrosynthetic analysis because it's just a very common type of problem. You know what you want to make, and you can use an aldol condensation to do it. You just have to figure out which one is good and which one will work well without giving you a lot of side products. Okay, uh, so that's all good. And this is kind of the basis of what this whole chapter is about. This is like a new sort of reaction. It's still like attack onto a carbonyl from a nucleophile, but now the nucleophile is this more interesting thing, and we could do a whole bunch of stuff with that more interesting thing. All right. So the way that, let's see, the chapter goes through it, maybe, all right, maybe I'll talk about this. So there's this like kind of interlude about alpha halogenation, which I guess is like fairly interesting. Um, and then I guess we'll get back to talking about this stuff in like the real detail. So for alpha halogenation, this is kind of like some good background and stuff to set up for it. This is like a good way you can use these reactions. Uh, if you have like, let's say CH3 here, and you give it a halogen and a whole bunch of base, then it'll halogenate a whole bunch of times. Okay. And then this CX3 is a pretty good leaving group. So from there, you wind up getting an acid and HCX3. And this reaction is called the haloform reaction. Okay. And maybe the term haloform sounds a little bit familiar. Like, uh, so if you did this, like, it's called the haloform reaction, and you can use it to make various of these like haloforms. Okay, so you can use it to make like iodoform, and the book talks a bit about that. You can use it to make bromoform. You can use it to make chloroform. Okay, maybe you've heard of this one. So this is good for like all of your kidnapping needs if this is your sort of thing. Uh, and yeah, you can use it to make these. Nobody talks about fluoroform that much. You don't deal with fluorine that much in this class, so don't worry about it. But like you can use it to make these, which is kind of good, and you get an acid out of it, so that's kind of helpful too. Okay. Uh, if you do it with acidic, then you only get one halogenation. Okay. And there's another thing that you can also do, which uh, your professor loves to talk about. So if you use bromine and PBr3 on an acid in particular, then you wind up getting alpha bromination. Okay. So this is the Hell-Volhard-Zelinsky reaction, or HVZ for short. Okay. And there's a really cool thing in the book that says like, oh, you can use this reaction to make amino acids because from here you could just swap out this bromine with an NH2 and there you go. You've made an amino acid, like the biological kind, which I don't know. I thought that's pretty cool. If some of you are like biochemistry people, then that's kind of neat because you can swap out this bromine and make an amino acid, and you can make like artificial ones and then put them in organisms and make them do cool stuff. Okay. All right. So that's all there is about halogenation. I guess it's a neat thing, but like maybe not the most relevant. But I don't know. I guess I'll try to stick with somewhat of the order that the book follows. I want to make sure I hit it uh, at least somewhere. Okay. Cool. And from there, uh, Yeah, okay. Maybe, right. Yeah, this halogenation thing was kind of a weird thing to stick in the middle. I probably should have like figured out the order a little bit better. But so earlier I was talking about retrosynthetic analysis, and like this is the main type of problem again that you'll see. Okay. So let's say that we want to make this compound. So here's like an example. Uh, if we wanted to synthesize this compound, then we can go backwards, right? And the way that you do that is you look at the alpha car or whatever, wherever your carbonyl is, and then you go to alpha and then beta, and you want to break the alpha beta bond. Okay. In these cases, you're always making an alpha beta bond. So you know that you can break that bond to go backwards, right? Meaning from this structure, we can go back to like something that's like over here, and then something that's over here. Okay. So here is our alpha carbon. Here is our beta carbon. Okay. And we know that there's going to be a hydrogen here, and then we have a carbonyl on this one. Okay. And in this particular case, what would happen is you would take these two and put them in some sort of base or acid. You could use whichever one you want. All right. Uh, this thing has no reactive hydrogens. So, okay. So this one won't do anything, the one on the left, whereas the one on the right has two reactive sites. But because of sterics, in this case, we're going to use the one that's over here on the left because it's less hindered. Okay, it'll be the much better nucleophile in this case. So, all right, we put them in some strong base. You get an enolate. This enolate goes in and attacks. Uh, Onto there, and then we pick out an H from some water. Okay, so from there, you get this structure, which again, this is a beta alcohol. And okay, that's good. And from there, you just do the same thing. You either use acid or base, whichever one you had it in earlier, and you just heat it, and that does E1 or E2, and it gets rid of that OH. Right? So this is how you would do like the sort of retrosynthetic analysis problem. You look for the alpha and beta carbons, you break that bond, look back at what you get, and then from there you can see how the reaction went forward. Okay. Uh, and the book also talks a whole bunch about how you can use this to cyclize things. Okay. Uh, it's the same reaction. It's just now you have both of these carbonyls on the same molecule. Okay. So instead of giving like a random example for this, I will actually just pick one of the ones from this week's worksheet. So I will use problem 2b because it's actually precisely this. So let me take 2b and put it into this document. Now move it over to here. And I got a little bit more advanced now because I learned how to scale these things. So now I can make it bigger. Uh, Okay, there we go. So if we look at this reaction here, uh, if we try to go forwards and just like think starting from here how this would work, uh, it'll be complicated because the structure of the final thing that we have really should like will help tell us what process happened. Okay, so over here you have a carbonyl, an alpha carbon, and a beta alcohol. Okay, so we know exactly what to do. We're gonna take that alpha beta bond and we'll cleave it, right? And so working backwards, what we know is that this thing must have come from this enolate. Okay, you guys see how I did that on board? Yeah. If anybody has any questions at any time, like always, you can interrupt me. You can send a private message. You can send a message in the chat. I have it like the chat open on another screen, so you could always interrupt. Um, well, okay. So we have this thing over here, right? And well, here's an enolate. So this enolate came from using a base, and I'll just say LDA because it tends to be the good one. Uh, on this thing, okay? Maybe I can redraw it a little bit more suggestively, right? And draw it that way, okay? And now, hopefully, at this point, we might be able to see how we get from here to here, okay? Uh, because we have this double bond and we want to replace both sides of the double bond with a carbonyl or like a ketone and an aldehyde, okay? So what's our go-to reaction to do that?
Ozonolysis.
Yeah, there we go. Okay. So ozonolysis, right? O3, then give it dimethyl sulfide. There you go, ozonolysis, right? So you do ozonolysis to get these two carbonyls. From there, LDA to get this enolate, and from there, well, you don't have to do anything. It just does it by itself. Okay. Uh, this just happens on its own. Okay. Uh, yeah. I guess you put it in water if you want, but like whatever. Okay. So there you go. That's problem 2B. Okay. And all that we really did is we just split the alpha beta bond. All right. And from there, we were able to see what we started with. So we knew how to get to what we started with because that was just old chemistry, stuff that we've seen a long time ago. Right. For each of the reactions that we talk about, there's kind of this like cyclization variant, but it's the same reaction. It's just using it to cyclize, which isn't like it's not any different in terms of the chemistry. It just winds up making a product that looks a little bit different. Okay, cool. Then from there, you there's a section about when you take an ester plus an ester. So you have like uh, here's your ester of I don't know one sort, and then here's your other ester. And let's say you make an enolate here, and okay, now this enolate attacks. Maybe let me draw this one in red. Now this enolate comes over here and attacks, and okay, we kick off that RO minus, and from there, what you wind up getting is what is called everybody's favorite. So this is a beta keto ester. Okay. And well, I guess these are kind of a big deal. The book likes talking about them. Yeah, I guess they're kind of interesting, but like this is another one of those sort of final compounds that like you can uh that like if you see it, you kind of can go back and see where it came from. Okay. Oh, David asked a question here. Uh, do we get two products? Yeah. So in this case, I kind of so I kind of noticed that here. This enolate would uh yeah, you could probably also like take off a hydrogen from over here and do something else to get to this product. Yeah, I think you probably would wind up getting two products from it. Um, yeah, which yeah, I guess you would have to separate them unless anybody can think of like a way to do this so it's selective. But uh, I think you just have to wind up with two products. Like there's not much of a way to avoid it in this case. I think. Yeah. So yeah, I guess you would wind up with two products, which kind of like, kind of sucks, but like with these reactions, you kind of have to live with that sometimes. Um, there are ways to like prefer one product or another, but you won't always get that.
Could you like in that last problem,
Yeah.
could you do like an ester and then it forms a ketone again and then like figure out a way to selectively reduce it?
Oh, that could be interesting. Yeah, so like one maybe option would be to do maybe get like a carboxylic acid, uh, and then like a ketone over here. Make this into an ester, and in that case, you would actually like preferably make the ketone an enol, and from there you would get but then you'd get two ketones, and how do you selectively produce one of them over the other? Like they'd be equally reactive, so it would be hard to say like I want to make this ketone into an alcohol and not this other ketone. So that's where this one would run into problems. Um, yeah, so this way won't wind up working out because you just can't get that alcohol selectively.
Could you also have, for the product, the molecule that you drew right after the product, could you have also put the negative charge at the end on the methyl group?
So yeah, uh, but the thing, if you did that, let's see. So if you did, oh, I should have given myself more room. Uh, so if you did that, then you would wind up getting a one, two, three, four, five, six, seven membered ring. And uh, for reasons that be, making seven membered rings is a lot more challenging than making six or five membered rings. Particularly through this method, uh, you generally find that seven membered rings really don't show up. So you could make a minus charge over here, but this probably won't react with itself at least. This could react with like another molecule of this, and then you get like way more complicated stuff going on. But with itself, it probably won't react. Yeah. Yeah, so that's all. I guess that's another thing to look out for too. Uh, you'll always prefer to make the 6 or 7 membered ring, not, or sorry, the 5 and 6 membered ring, not the 7 membered or 8 membered ring or 4 or 3. Um, those, yeah, those are a lot harder to make for like entropic reasons, and that gets more complicated. So generally, you're just restricted to 5 and 6 membered rings. Okay. So over here, well, I guess I should ask any remaining questions up here in 2B. Okay. Okay. Uh, yeah. So down here we're making a beta keto ester. Uh, and when we're doing that in particular, this reaction is called a Claisen condensation. Okay. Claisen was, I don't know, I guess the person who figured this out, so good for them. Uh, but it's more or less the same chemistry. It's just now we have two esters and one of the like RO minuses gets kicked off. So we just make a beta keto ester. But otherwise it's the same like process. And again, you can use this for cyclization. Okay. And in this case, it's specifically called the Dieckmann condensation, I think. Uh, I don't know if I spelled it right, whatever. It's just a name, but it's the same reaction. It's just doing it intramolecularly now. Okay. So, for example, what this might look like, there's no example of this on the problem set, so uh, I just made one up. So, like, let's say we wanted to go from here to what's in the final structure? Oh, I guess this problem's a lot more similar to the last one than I thought. I thought I was being creative with this. Maybe I wasn't. So it's something like this. Okay. So we're gonna do the same thing. All right. Here's our ester. So we go alpha, beta, and we break this bond. Okay. So we know going backwards that we must have come from an enolate that looked like this. Okay. Here it's this ester because we had to kick that ester off. All right. And exactly what's over here is like uh we don't know exactly what ester it was, but like it we can say O-methyl just for the sake of things. Okay. So we have two carboxyl groups again. So an easy way to do that from over here is to make or is to put it in hot potassium permanganate, which will give us two carboxylic acids. Okay. And now we need to turn these both into esters. And ideally, we turn them both into even methyl esters because our final product is a methyl ester. Okay. So what would be a good way to make both of these into methyl esters?
CH2N2.
Yeah, there we go. Okay. I was looking for that one in particular. Yeah, so we use diazomethane. Okay. You could do a Fischer esterification, but diazomethane is way nicer because like everything gets converted very well, like with a very high yield. Okay. So diazomethane would be a good way to do that. And then once we have those methyl esters, we can just put it into some sort of base. And when you're doing this, the usual base that you use is the deprotonated alcohol that your ester is. Okay, so basically in this case you would use O-methyl minus as your base. Okay, because that way if your base attacks onto tacks onto your ester, it won't really matter because it's just going to swap out an O-methyl for an O-methyl. So like, hey, that's fine. Um, so this is like this is a good way of synthesizing, right? So we just go split that double bond into carboxylic acids, similar to before. Now we want to turn them both into esters, so we do the best way that we know how, and we make them methyl esters. Then from there, you make the enolate, and bam, one step, this just happens. Okay. And this is what you could call a Dieckmann condensation if you want. It's the same thing as, it's just a Claisen concentration, but a Claisen condensation, but it's in the same molecule. Okay. And cool. So from there, uh, oh yeah, the book has some stuff about like mixed Claisen condensations. He talks about it a lot. Like, yeah, there's a whole bunch of stuff about mixed Claisens. Uh, I mean, you can read about it. The idea is just that you want to limit the number of reactive hydrogens that you have, because the more reactive hydrogens that you have, the more complicated things will get, right? The more places you can react. So ideally, you pick molecules that only have one place that you can react with the hydrogen, and well, then you're good, right? Because you know what will happen. So yeah, there's some stuff about mixed Claisen reactions. I didn't think it's very interesting. Yeah, I don't know. Maybe if some of you are like genetics people or something, you like talking about crossed Claisens or something. I don't know, whatever. That might be your thing. Okay. Uh, from there, there's this thing called the malonic ester synthesis, which is a very like useful way of doing things. So the idea here is just that like whenever you want to make substituted acetic acid like this, okay? So whenever you want this thing, then you can do that. You can make this just by having like halide or tosylate on your thing, and you use something that is like called malonic ester, which uh, should look something like this. Okay. And there's these hydrogens here, and like I said at the start, like these are super acidic. They will come off very easily. So you do that, and then one of these like whole sides winds up coming off as like carboxylic acid because you just heat the thing. And that's really nice because then you could just basically stick an acetic acid on to whatever you want. Just like from the carbon-carbon side, which is like kind of interesting. Okay. And the same thing goes for the acetic acid or acetic ester synthesis. Okay. It's the same idea here. So if you want to make substituted acetone, then you can go backwards and use acetic ester, which looks something similar to this. It's like the same thing, except one of the sides is just acetone, not an ester. Okay. So when you see these two things, like this is they're common enough syntheses that like they're like, they're named. They're very common. So when you see like an acetic acid hanging off of something with the rest of it there, or like you just have an acetate hanging off, then that's like that might indicate that one of these syntheses was used. Okay. And they're nice because CO2 gas comes off, and CO2 gas coming off is irreversible. So that's always like a big plus. Okay. And then let's see. Okay, I've still got room. Uh, and then the last thing, which some people even ask me to talk about, which is good. Uh, is the Michael addition. And this is a pretty interesting reaction because always what you've learned is that like let's say you have I don't know this enolate, right? And normally what happens is okay, how about I say let's say we have this enolate and this carbonyl. Okay. So normally what happens is we take the electrons and they usually go over here. Okay. So this is what we've seen before. Uh, okay. But what happens in a Michael addition is instead that these electrons will come up to the end of the double bond and this will kick the electrons up this chain because this is conjugated. And it'll move them to make in the same way that you would move the electrons like up onto the carbonyl normally. But now we're just doing it from farther away. Okay. So here, instead, what we've made is this bond and then O minus the same way, like normal. Okay. It's just now it's farther away. Okay. So this is the bond that we made. Right. And from here, now we have an enol. Okay. And bam, I mean, once we have an enol, then that will just turn back into a ketone because we have the keto-enol tautomerization. Okay. And if you want to count about carbons, then from here we have alpha, beta, gamma, and now we have delta. Okay. So if you want to make delta ketones, then this is the way to do it. Okay. The other way to say this is that instead of like a, let's see, like a 1-2 addition, you have a 1-4 addition. Okay? So you're adding onto this carbon down at the end here, and you're pushing your electrons up the chain. So to do this Michael addition, you need to have a conjugated double bond. That's the important part. Okay? And in this case, what you would say is that like this thing is your donor, and then this conjugated system is your acceptor. Okay. And well, the difference between donors and acceptors is just something that you've seen a whole bunch before. All right. Here, this donor has a lot of electron density. And here, the acceptor is a very withdrawn double bond. All right. And lucky for you, you spent this whole class talking about electron donating things and electron withdrawing things. Okay. So there's a whole table about donors here. So like a very common one is to have organocuprates is a big one, and then like all of the other things that we just talked about in this whole section. Okay. So like this thing is a very good Michael donor. Uh, like yeah, and all of these various enolates and also enamines are all good Michael donors. And then from here, you just have withdrawn double bonds. So this ketone is very strongly withdrawing. An ester is strongly withdrawing. An amide is withdrawing. And all of these like carboxylic acid derivatives that you've just spent so long talking about well, this is it. Like, these are the ones that you use. Okay. Uh, there's also like a nitrile and an like a nitro group, and yeah, I guess those are relevant too, but you don't need to worry about those like so much. Okay. That's the whole deal with like Michael donors and acceptors, and like with all of the other ones, you could do cyclizations. Okay. And this one is called the Robinson annulation. Right? And the general way that this looks is whatever you get at the end is going to be like this. Okay. With a double bond there. Right? And I don't know, maybe let me just yeah, okay, we'll go yeah. So like the book has a I think the book actually has a good example of this one, which is like not common for the book. But the one that they have is if you take this structure down here and you give it this same conjugated system that I've been doing this whole time, right? So you form an enolate here, kick this up the chain, okay, and then you have your ring. Let's see. Uh, yeah, there we go. Okay, so it looks like that. And oh, there should be like another thing here, I think. Yeah. Um, yes, yeah. So it looks like that. Okay. And then you form your enolate over here, which will give you an alcohol hanging off there and a ketone. And then you hit it with more acid and it makes a double bond. Okay. So same idea with this as with all of the other reactions. All right. You have a ketone. All right. You have this ketone. You find the alpha beta bond and split it there. Okay. And you saw in this case that alpha beta bond split to be a carbonyl. Okay. So in this case, splitting it made it look like a carbonyl. And from that carbonyl, you can see where it did a Michael reaction. Because here it's like you could count it if you want, and it's alpha, beta, gamma, delta. Okay, great. Okay, so let me save this thing. Uh, Save that. Okay, and I think from there we will start answering some questions from like the worksheet. So here we go. Let's open up a new document. While I'm pulling this up, does anybody have questions that they want to ask? Anything? Well, if not, I mean, we will have plenty of problems to go through, so what is this? Okay, all right. I thought I knew what I was doing before, but I felt real good about myself because I learned how to scale pictures, and now I don't know what I just did. So, okay. What's up? Okay, somebody had their microphone on. It sounded like someone was going to say something. Okay, so the question is to synthesize this thing using some sort of condensation. So how about I maybe actually, since I'm all powerful in Photoshop, I will actually just redraw this so that it's more meaningful, like right onto this thing. So let me get my pencil back. Whoops, that's in red. Here we go. So this is what we're working with. Okay? And so we've got an ester, and here's a beta ketone. Okay? So we have a beta keto ester, and which reaction makes beta keto esters?
Claisen.
Yeah, there we go. Okay. So a Claisen condensation does. Okay. And well, what that means is that we should go back and start with an ester. So, okay. So we have this ester here, so let's go alpha, beta, and then cut it there. Right? And cool. So then let's go back. Retrosynthetic analysis arrows, which will be really the only arrows that I draw today. Uh, so there's that carbonyl on the left, and over here we've got this other one. Okay? And well, it doesn't really matter what ester we put over here. So this could be I don't know, I'll call it R because like it really doesn't matter. It's gonna get thrown away at the end. So it won't really make much of a difference. So whatever, call it OR. Okay? And then from here we could take this to go forward in the forward direction. We can put it in some strong base, which in the case of a Claisen condensation, the most common one is to use the ester that remains. Uh, so we'll take this ester and use it as our base. Okay. In this case, that is, we take O-ethyl or sodium ethoxide. Okay. And that's our base. So this is done also in ethanol. Right? And there we go. Okay. So, well, maybe what we do is, all right, I'm just gonna erase things and redraw because, whoops. Uh, what I was going, oh man. Yeah, what I was gonna try to move the stuff that I already wrote, and then I realized that things could go horribly wrong because I don't actually know how to do that. So, all right, so we take this thing and then put it in uh, sodium ethoxide in ethanol, which will make uh, this, okay, and then from there you can add these two together and you get product. And Becca is asking if we could have done something with the acetoacetic ester synthesis. So for that synthesis, whenever you do that, uh, so the yeah, so that one will always wind up producing acetone that has the rest of the molecule hanging off. Okay? Uh, Particularly because, well, even if it doesn't, so even if we don't do that heating step and we keep the rest of this on, then we get this as our product. Okay? And really, you will only use this reaction, and same with the malonic ester synthesis, if your product will look like one of these two things. Okay? So the reason in this case that we didn't use the acetoacidic synthesis, this naming is terrible, uh, is because in this molecule we don't have something that looks like that. At least, well, I don't think so. So,
I was
oh,
thinking like the cyclic pentane could be like that R group. And then,
Okay, yeah, I totally see what you're talking about now, right? So let's say you, yeah, so maybe an alternate synthesis of this molecule would be if you had, uh, like this six-membered ring. Uh, let's see, how do I zoom? There we go. Okay. Uh, so if you had like this six-membered ring, and then yeah, yeah. So this would be an option, particularly if you have, yeah, if you have this sort of compound lying around, then yeah, totally, right? And then you could use like O-tosylate here or something, right? Something that'll come off fairly easily. So yeah, you could do it this way. Uh, in general, it's probably going to be assumed that something like this is uncommon, like this thing. But this synthesis would work. Yeah. Um, this would be like a viable option. So yeah, you could do it like that. Okay. And let me get the next problem on, which is B. Oh, I kind of like B. This is a nice problem. All right, let me go find it. Okay. For a second there, it didn't move. All right. Oh, and I can scale it too. Let's make it nice and big. Oh, yeah. Okay. There we go. So now we want to make this one, and you'll notice, okay, it's actually not very interesting. It's kind of the same thing, right? I want to zoom. Okay, there we go. Yeah, this isn't too exciting, right? It's sort of the same. So we have an ester here, and then alpha, beta. So it's a beta keto ester. And okay, let's cleave that bond and work backwards. All right. So working backwards, well, pick whatever ester you like. Let's do O-methyl because it's the same as the other one. Plus this O-methyl, and all right, now there's a whole bunch of other stuff hanging off. Okay, and so it came from this enolate. All right, great. There you go. That's it. Okay. This the trick of like cleaving the alpha beta bond is like the most effective way of doing these problems. Okay. Uh, However, maybe I should mention before uh, Becca calls me out again for not being thorough enough. Uh, you could do this another way. Okay. So if you happen to have this whole top thing lying around, then I mean, yeah, you could definitely do this with this thing, this enolate over here, and then you need the bottom part also. So you need something that looks like that. Okay. And you need something to get rid of off of there. So how about we put bromine? I don't know, right? Just pick your favorite leaving group because this thing is a good nucleophile, so it'll kick off whatever leaving group you have. Okay? So there you go. That's another option that you can do. Great. Uh, if you're really like paying close attention, then there's yet another third option that you could actually do in this case. Okay? So one more thing that you could do is instead of cleaving the bond there, you could also cleave the bond here because here's a ketone and here's another ketone. So this is something that you could do, and this is the green path. Okay, and over here we did the blue path. All right, and If you take the green path, then what you do is you redraw everything before it was cleaved, or once it's cleaved, and now you have this O methyl here, and you need to get rid of an OR, like an OR, an O something off of this thing to get a ketone at the end. So if you want, you could also use this thing, which has two O methyls on either side of a ketone here. This is another option that you could do. This is weirder because this sort of compound is kind of uncommon also, but like this is totally fair synthesis. Like this would work. This would get you this exact product that you wanted.
Hey Adam, on the
Yes.
black path, you would have to do that as a two-step, right?
So here you would have to go, let's see.
Because your strong base would attack that like halogen
Yeah,
thing. Yeah.
yeah, I agree. So you would
Okay,
first
cool.
have to do LDA. Whoops. Actually, well, you wouldn't even need LDA. You could use like, let's say some large base, right? If you really wanted, you could use like this bulky base because it's basic, or this is a very acidic hydrogen here. So you could use some sort of bulky base. It's kind of hard because there's an ester here too. So maybe you want to use a base that won't displace that ester, which, this OT-butyl might do. But basically, yeah, you're right. The best way to do it would be to first make this into an enolate, and from there add this thing. Add
So we
the.
couldn't use something like sodium hydride because it's too strong and it'd mess it up, or we could also do that.
It would probably work fine.
Okay.
Yeah, it would probably be a totally fair base to use in this case. It's a little bit overkill to be like to be practical. Sodium hydride is it's very strong,
Hmm.
so I think it would work, and and I think it would work fine. It's just a bit unusual because like this thing is already pretty acidic as it is, so you're using something that's like super strong on something that's already kind of, you know, it will readily give up its hydrogens.
Okay, thank you.
So, yeah, it's just uncommon, but there's nothing that says you can't do it, and it would totally work. Yeah. Okay, so this is like two steps that you would probably have to do. Okay. Yeah. Good. So maybe actually what I can do is whenever I take screenshots, what I can do instead is to move my thing over to the other screen. That way the previous problem stays up. Is, kind of a good way of doing this. Yeah. Really, really getting used to this whole online teaching thing. No, I'm not, but I'm picking it up. Okay. So I want to zoom again. There we go. Actually, no, I'm totally fine here. Okay. All right. Well, let's look at what we have. So, all right. Now we have two ketones. So here's one ketone and another ketone. Okay. And in general, when we have two ketones next to each other, then you know that you probably want to do a Claisen condensation yet again. Okay. Because that way you just get rid of that, like whatever's hanging off really, really quickly and easily, and you get a ketone right away. So, all right. So, well, then now we have two choices, and now we have to now we kind of have to think about which direction we're going, right? So, how about we do same thing as before, blue path, and and we'll also have a green path. Right? So let's say that we take the blue path and we go over to here. So there's an ester on this thing, and there we go. Here's, all this extra stuff hanging off that end. All right? So this would be our enolate, and it has to attack the ester over there. Okay? Anything fishy about this path? Anything look kind of weird?
Wait, would this have been the green path? Because if you're cutting, like you're
Oh,
bringing
did I?
the...
Oops. Yeah, okay, yeah, this totally was the green path.
Okay.
Whoops. Yeah, okay. So there was something fishy about it, which is that I just cut the entirely wrong bond. So, yeah, thank you. uh, yeah, there we go. Okay. All that extra stuff. Okay, and let me get rid of this other one. Uh, okay. Anything look weird about this path to anyone? Let me open this chat thing. No? Yeah, no, I don't think so either. This looks totally valid. Okay. Uh, the only thing that maybe you could say is that you might get some uh, some enolate over here on the ester too, but maybe remember that the pKa over here is 25 and the pKa over here is 20, right? And remember that pKa's work on like a logarithmic scale or whatever. So basically, you'll wind up getting 10 to the 5 times more, or 10, like 100,000 times more on this side. So basically, yeah, this will totally work fine. Okay, let me get rid of this. This is like not relevant, but uh, yeah, as far as I can tell, this looks like it will totally work fine. Okay, and then maybe let's try the other way. So let's cleave this other bond. All right, so we've got this, and then we have all of this extra stuff, and we need to make it an ester, right? So let's make it O-methyl. Why not? All right, and this will be our enolate back here. So anything about that looks weird? Silence? Well, no. Okay. This looks fine too. So, okay. Both of these ways actually would work then. All right. Some people would say that this is the blue path is preferred because there's only one possible enolate that does form, whereas so here there's only one possible enolate, and then here there's two possible. But the ester is like way less common. So, but not really, right? One of them will form way more often than the other. So this is like a totally fair way of doing it. So either one I think is pretty fine in this case. Yeah, in this example, either one should be able to work pretty well. Okay, let me take a screenshot of the next one. Yeah, here we go. Copy, paste. And now let's move this down to here. Okay. So now, right. So this is clearly a cyclization one because, well, we've got a cyclic molecule. Okay. And that could be kind of intimidating because whenever you do cyclic things, you have to really keep track of your carbons and worry about, how many carbons are in the ring, how many do you have hanging off, and all that. Okay, but the way we approach the problem is going to be the exact same as in all these other ones. Okay, here's our ketone. Find the alpha carbon, beta carbon, and split it. Okay. Uh, so that is the way to do it. Okay. So retrosynthetic analysis, go backwards over to here. Whoops. Okay, I didn't split it at all.
Wait,
Over
I'm
to
sorry,
here.
Adam, to interrupt again.
Yeah, no worries.
I was just in C, I was looking back at C, and in one of the ways, maybe I'm misunderstanding, but if we were doing Claisen, it's two esters coming together, right? So
Oh.
how
Oh,
would
okay.
only the like that? Maybe I'm misunderstanding, but would one of these
No.
not work? Isn't it like
Oh,
the
maybe
cross?
yeah, okay. Maybe I was mislabeling it. Uh, yeah, so the Claisen condensation I think is particularly when you have an ester and an ester. So
Yeah, that's what I thought.
in that sense, I guess neither of these are Claisen condensations. It's just a reaction of an enolate with an ester, which is like an not named, I guess.
So then, how do you choose the alpha and like what are you choosing to cleave? Because typically you like cleave the alpha beta, like alpha and beta of an ester in the molecule,
Yeah.
like in when we're doing the retrosynthesis.
So yeah, so if there's an ester hanging behind, then uh you know that ester probably wasn't the one that got broken. Like for example in B, right? We had an ester over here in blue,
Mm-hmm.
so we know that one probably stayed behind. But there's also this green path that we could have done which kept that ester around, but this is less likely. Okay? It's this is a less common way to do it. So,
Yeah, the blue makes sense because it's the alpha and beta of the ester. Uh-huh.
yeah. Um and in this case we don't have an ester left behind. We just have two ketones. So you kind of have to like try both of the options and see which one is more reasonable or which one will get you like less of a mixed reactant or mixed product. Like in this case, uh, people might say that the one on top is better because you only get one enolate, so there's only going to be one product. Although here you're mostly just going to get one enolate as well, so it's mostly just going to be one major product. But you kind of just have to test both of the possible ways in this case.
Okay, so this doesn't have to have two s like for C in particular.
No, no.
Okay.
Yeah, I think I was really mislabeling. When you do an ester, you'll wind up or sorry, when you do a Claisen condensation, the product will should wind up having an ester at the end as well.
Hmm.
Um,
But that's
so
not the case.
yeah, I think I was more just mislabeling this reaction. Okay. Does that help? Sorry, I was unclear.
Yeah. Yeah.
Oh, okay. Um, yeah, so this is just like going back to ester plus a ketone, as opposed to like over here where we were going back to an ester plus an ester. And this one up here was Claisen. Whereas this one down at the bottom is not Claisen, I guess. It's just unnamed. It's an ester plus a ketone. So condensation of an ester with a ketone, I guess. Okay. Um, yeah, okay. Thanks for asking. Yeah, I guess I was being unclear. That one's like that one's on me. Okay. So now for D, going back here, right? This one it's we have a ketone and there's no other ketones, so we know which one should be alpha and beta, and in particular there's that double bond there, which makes it like you know it's really right there for us to see. So we cleave that alpha beta bond. There we go. Okay. So now we have this thing to start with, and let's see. This reaction, this question is just how would we make this with aldol, Claisen, or other condensations? Okay. Uh, yeah. So presumably we're not starting with this compound over here because, well, that would be pretty easy, right? From here, we could just take, I don't know, whether you want to do it in acid or base, either one would work. So how about we just do it in base because, well, things tend to work better in base. So how about we just use hydroxide? Okay, we will get, oops, our enolate over here. Okay, which will attack over to here, and from there, that becomes an alcohol. All right, and then you just heat it with base some more. Okay. But, well, the question is how you actually make this thing over here. Okay, this is what we want to make. So, we have two ketones on the same molecule, and maybe one way to look at it, which is not the most intuitive, is that you have alpha, beta, gamma, and hey, look, this is a delta ketone. Okay? And delta ketones are super characteristic of a Michael addition. So that's one way you could think about it. You could do Michael addition. Well, or either way you think about it, you're going to wind up doing a Michael addition. But you can also look back at what you started with and just notice that this is like something that you'll pick up as you see more of these is that whenever you have this structure, this should scream that this was done with a Robinson annulation. Okay. So, yeah. So in the case of a Robinson annulation, that is always to do a Michael addition and then do a cyclization. Okay. So, we've seen our cyclization and now we just go backwards and do a Michael addition. Or to think about it going forwards, you do a Michael addition and then do a cyclization. But going forwards tends to be a little bit harder. Okay. So, okay, we want to synthesize this thing. All right. To do that, then we will start with this compound. Or, well, we want to make this compound. And the question is how. So whenever we have a Michael addition, we want one of our ketones to be conjugated, and the other one will be an enolate. So let's say we make this ketone the conjugated one, which should look like that. Then this other one, let me pick a different color here. This other one will be our enolate. So it will wind up looking like that. Okay. So then to go forward, what you do is this enolate will react here, do a Michael addition, and from there you wind up doing a keto enol tautomerization to change this the enol that forms into a ketone. And there you go. So then you get your delta keto ketone, right? You have your two ketones on the same molecule, and then from there, just cyclize. Okay. This wound up being a common enough reaction or an interesting enough one that it got a name. So it's called the Robinson annulation. But all we did is do a Michael addition of two molecules and then cyclize them. Okay. And the cyclization happens pretty much in one step. Okay. Questions?
Nope.
Okay, cool. Okay, I don't hear anybody. So, all right. Well, let me open up a new document. Start working on new, and okay, here we go. So let's pull in something from 2A. All right, here we go. Scroll and move it up. Okay. Here we go. All right, so here's 2A, and okay. Great. So now let's take a look at this, and all right. Well, here's something that you might notice if you look at it. We've got this alcohol here, and it's right next to this double bond. Okay. So maybe if we were just a little bit luckier, then, you know, we would have had alpha, beta, and this would have been a ketone. Okay. But, well, fortunately we can do that, right? Because we know how to go from ketone to an alcohol pretty quickly. You just reduce it. So we can go backwards and have this be a ketone, right? Forwards, you could just reduce it. So, you know, use your favorite reducing agent, minus sodium borohydride. So how about we use that one? Okay. Oh, yeah, here we go. And now what do you notice? Okay. You notice that you have this ketone and a double bond right next to it, right? And what reaction does that just tell you we're going to do?
Robinson.
Yeah, there we go. So, yeah, this is going to be a Robinson annulation because you have this whole six-membered ring, especially, and it's got a ketone and a double bond right there next to each other. Okay. So, good. Yeah, then we'll go right ahead and do it. So in that case, we know for a Robinson annulation, or really for all of these things, that you take alpha, beta, and cut it along that line. Okay? So then let's go backwards. Right? So we will have this ketone there, and then another ketone over there, right? And this will be our enolate that we wind up making, right? And from there, it makes the alcohol, and then from there, the alcohol gets dehydrogenated, or hydrolyzed, whatever, I don't know. Okay, whatever. I'm blanking on the term. DH2O. There we go. All right, that works. Okay. You do E1 or E2. probably E2 because it's in base. Okay. So there we go. We know what we're working with there. And now all that we have to do is just figure out what the Michael addition was. Okay? So we're starting with this thing. Oops. So we start with this thing. Okay? So you know that we can just make an enolate over on either side of that ketone. Okay. And then from there, you can add some Michael acceptor of your choice, right? So we know that it's going to have to be a conjugated ketone, and then we want to include the rest of this side over on it. So how about we, I don't know, make it green? So we want to be sure to include that, okay? So we'll include it over here. Okay, and it just looks like that. And there we go. Michael addition onto this thing, which will wind up forming this because you'll regenerate your ketone. And there we go. From there, you just add base. Yeah, you add base and it makes the alcohol. So it's cyclized. And you take the alcohol off, and there you go. And then you could reduce from there. Okay. Any questions about this one? This is yet another Robinson annulation.
Would we be able to switch sides for the donor and acceptor?
Sorry, what was that? Oh,
Could we make like the other side the donor?
so for the other side to be the donor, then we would have to do something like this. And let's say we would, let's see, how else could we
Could we
do
instead
it?
have like a methyl off of the ring and like make that a double bond?
Yeah, so let's say we did that instead, and then we would cut it over here, so then it would look like this and a minus there. Okay, and from there it would take that down, move there, okay, and we wind up with the same product. So, yeah, I think this would work as well. The issue here is whether you would get this enolate versus the other one, that enolate. And sometimes you're able to kind of like control which of the two enolates you'll wind up getting, but in this case, there's not much. Like these will probably form in fairly like similar quantities. There's like a slight steric argument for this one, but it's not too much because this methyl group hanging off isn't gonna like totally make this a worthless nucleophile. So it'll still kind of work. So this is kind of like yeah, I just think this is the challenge with doing it with in this direction. But besides that, I don't think I can see anything that would go wrong there. Yeah. Unless maybe anyone else could, but I don't think I can. Okay. Okay. Any other questions about 2A?
I just put this in the chat, but can you use a base like NaOH, or do you need something stronger?
Use something stronger. So, you could always use something stronger. Like that's always an option. the reason I think I went with NaOH was because that one would be like reversible here. So if you use something like LDA and you took the hydrogen off this side, then you wouldn't really be able to undo that. And you're not going to react with this thing over here, but it'll react with like another one of these whole molecules elsewhere. And then you get more complicated stuff. Maybe. You could totally use a stronger base though. Yeah, nobody would say that's bad. So yeah, that should be okay. Usually, like also just practically, people try to use. I guess people would try to use like weak, milder bases if it's an option. And in this case, the cyclization will happen kind of like fairly readily, so it doesn't need to be like crazy conditions. Right. Here we go. Okay. So let's get 2B. Oh, hey, we did 2B. So I'll just write as a note. So if anybody like goes back through and looks at the notes later for reviewing or something, then yeah. We already had 2B done, and yeah, and you can go back and find that one. Okay, cool. So let's paste in 2C. We're almost done, at least with problem 2, and then maybe some of you have looked ahead and noticed problem 3 is a genuine abomination. But hey, we'll get there. We'll get there in a second. All right, here we go. Okay. Now we have this phenyl ring, and oh boy, we got to make this whole big thing, and that's kind of like looks like it'll be a pain. Okay, but well, by this point, you've noticed. All right, here we go. We've got this, right? And that means you know what we did. We did a Robinson annulation. Okay, so leave the bond. Okay, go backwards, so we cut that bond. And there we go. That's what we went back to. We also know that this was the result of a Michael addition. So all right. So we had an enolate over here and our Michael donor over here. Or sorry, our Michael acceptor. So what we started with looked something like, this plus this conjugated system, right? Yeah, so it looks something like that. Okay, and now the question is, how do we make this thing? And fortunately, I think that making this whole thing is all old news, all like old reactions that we've done a lot of before. We've seen a whole bunch. Let's see if yeah. Okay. Anybody have any ideas about how you actually make this thing?
Can you do it with some kind of palladium coupling? Or no?
Oh boy.
I tried. It didn't work well. So
Okay. Maybe you can. Although, let's see, you would need some sort of like bromine or halogen or something, I think, right, to do palladium coupling. Uh, so
Is it possible to start with like making a carboxylic acid on the benzene?
let's see. So let's say we go forward and we make like a carboxylic acid. Okay. And then from there, we're gonna need to get rid of this OH somehow. So how about we do like use SOCl2 to make it this chloride, and then why don't we from there? Let's see, what can we do? Why don't we? We would need to add some sort of thing that can attack onto here, right? And the things we know that can do that are like cuprates and lithiums and grignards, right? So how about we just use like a cuprate with all the rest of our carbon chain stuff hanging off. Um, okay, so from there we could do like 1, 2, 3, 4 carbons. Uh, yeah, and then we get stuck here. And getting from this to the final product will be tough, will be iffy. Yeah.
What if you did like an acylation first and got like one of those like long ketones? Then you blocked the para with like a sulfur, and then you did like diazotization at the ortho and like put something on that like cyanide, and then you turn the cyanide into something that you can do.
Yeah. So let's see. Okay. So we can get to here with yeah, I see where you're going. Uh we can get to something like this with aluminum trichloride, okay? And we can also put something else, right? We can't put an acid there because it'll react with that chloride. So okay, we got to put like an aldehyde or something, right? So okay, we've got this aldehyde. Uh, okay, and maybe now from here you can do some oxidation and all right, now you have an alcohol. Okay, SOCl2. So now you have everything and an acid chloride. Okay, and all right, now you have this acid chloride. So let's see, what can you do? Oh, but now if you do like aluminum trichloride, then you're gonna wind up with two ketones. And that won't work, right? Hmm. Okay. Now what are we stuck with? Uh, I think so maybe you could see the point I'm kind of getting at here is like, there's not like a clear, correct way to do it. And it'll get a little bit complicated. Uh, one thing maybe, yeah, let's see. So one way that you could do it, this is one way. I'll show you another way in a second that's like the answer key way, which kind of uses something that like we haven't seen before. So, you know, whatever way you can think of would work. All right, so we've got this. Now we can reduce with the Clemmensen reduction. So zinc and mercury and HCl, which will get rid of the ketone but not the acid because the acid is too oxidized. Okay. And now use SOCl2 to make an acid chloride. And from there, you could do Friedel-Crafts acylation. Okay. And you don't have to worry about the whole sulfonation thing to do like para blocking because uh, basically there's no way that you're gonna wind up producing something that looks uh, I don't even know how to draw it like this. Like this is totally you know para would be like there, right? This is not yeah, this definitely won't happen. So I've certainly never seen anything that looks like it. So okay, this won't happen. So there's no need for para blocking. Okay, this is one way you could do it. Uh, Actually, the way that the like this answer key suggests is truly the same thing, more or less. Uh, so it basically just says you could start off with this, and if you use this anhydride, then yeah, it starts off looking like that, and so you can use aluminum trichloride. Uh, so if you use this, then it'll give you this acid right away. Okay. And from there, you do the exact same steps that we just did. Right. This is like, I don't know. I didn't know about this. This is like, I guess, what happens if you use a cyclic anhydride to do Friedel-Crafts acylation. I wouldn't worry about this so much. I think it was like one extra step compared to what we did. Uh, so it's an option. Whoops. It's an option, but like you could really go with what we had. Okay, which was take what you started with. You can use this special thing to do Friedel-Crafts, and then from there turn it into an acid, and you do all the same steps. So Clemenson, turn it into an acid chloride, do Friedel-Crafts acylation onto there, and then okay, now you have this thing which turned out to be surprisingly hard to get, and now you can do a Michael addition and you know go to town with your Robinson annulation. Okay. Cool. Questions?
What selectively oxidizes an aldehyde but not a ketone? Could you just remind me? Like
So
the first step for benzene. Yeah.
a ketone is already fully oxidized. So it won't make so much of a difference what we use, right? Aldehydes will be easy to oxidize, and then you can't really oxidize a ketone much more. I mean, not without like turning it into CO2 or something. Um, so yeah, we could hit it with bleach. You can use sodium dichromate if you want, whichever ones you want. Also for aldehydes, I think there's like you could do like basically the tones test, I think, which is like silver oxide, right? And then you like heat it or something. Uh, and that one's definitely only strong enough to oxidize aldehydes. If you really want to be like very particular, then like that would be one option. Okay. Anything else?
Can you scroll back down to the keyway again?
Yeah.
Thank you.
Yep. All right. I will. Oops. This. So yeah. Let me save this. Okay. And leave it up for a second. Whoops. Oh, so okay. So for number 3, if anybody has looked at it already, this like is one of those like roadmap reaction things, and it's like nuts. Uh, open? No. Okay. All right. Well, let me open it directly here. Then, Yeah, so it's like totally nuts. It's all over the place. So I basically went and like it's split up into pathways like A, B, D, and C, A, B, C, and D. And so I like went and cropped those out individually to make it a lot more manageable and reasonable. Okay. So, all right, let's work through this one and we'll see where we get. Okay. All right, we've got an acid and we're giving it SOCl2. All right, nice. We've done this a whole bunch of times before. We know that makes an acid chloride. Okay. We're not going to worry about this thing because that's for another pathway. Um, yeah, so we have this acid chloride here. All right, and now we give it ammonia. Okay. Uh, so you know that it will. Ammonia is a good nucleophile, so it'll take off that chlorine. Okay. And let's see. So there's an NH2 there that's stuck behind, and we're not going to replace that the C double bond O with a C double bond N. Mostly because that would include having two nitrogens on the same carbon, which would get pretty messy. So okay, let's keep the carbonyl there. And all right, now what do we have? We have chlorine and base, and we lose a carbon dioxide. That's very interesting. Let's see. What? Anybody have any ideas about what'll happen? Not sure if this is really a reaction that we talk about. So okay, I'll write it down. So we wind up getting
Is
this
it
as
alpha
a
halogenation? But or does the N interfere with that?
yeah. So I thought it would be alpha halogenation, but this is the product that you wind up getting, which is weird, right? I think this might just be a reaction that we haven't covered. Um, I don't know. This is weird. Yeah. All right. Well, okay. I won't focus on it too much. I do. Yeah. I think it's something that we just haven't really talked about very much. Maybe there's some complicated mechanism that we could really work out if we wanted, but no, it's okay. Uh, yeah. It probably goes like uh, alpha halogenation, and then some sort of like intramolecular, uh, like kicking this thing off and kicking off the chlorine too. But yeah, we won't worry about it too much. Okay. All right. So we have the. Let's go back up now. We have this acid chloride, and we give it sodium azide. This thing N3, and this N3 is a good nucleophile. So okay, we have a good nucleophile and something that comes off easily. So there we go. All right. And from there you can heat it a bunch, which will get us. Okay, this is a weird. Yeah, this is some weird problems. This is also not a reaction that we've really seen. All right, let's uh, not worry about this so much. Yeah, it looks like this, and then you can do that and get this product. I don't know. Okay, yeah, I did not see this earlier, so this is weird. And then if you add methanol, okay, the product winds up looking like this. Okay, yeah, this is weird. All right, let's yeah, let's move past this. This is a weird problem. Okay. Instead, how about we do B? B might be better. All right. Uh, let's see. So here's whoops. Okay. Let's use the product A1, which we had before, which looked like this thing. Okay. And then give it toluene, which is this guy. Okay. And aluminum trichloride, and it'll do an ortho substitution. All right, cool. This we've seen and worked with. Okay, lithium aluminum hydride and then water. Okay, so this is a reduction. So we're reducing our ketone. That's the only thing that we have to reduce. So it turns into an alcohol. Okay, cool. And then sulfuric acid and heat. This is bold, so this is E1. Okay, so we're doing an E1 reaction. There we go. So this thing winds up turning into a double bond. Okay, and this E1 goes very well because it's benzylic and all that. Okay, so here we do E1. Nice. Okay. We have osmium tetroxide here. Okay. Does anybody want to remind me what osmium tetroxide does?
Dihydroxylation.
Yeah, there we go. Okay. Yeah, so it does dihydroxylation, specifically syn dihydroxylation. Okay. So there's an OH and there's a syn OH and there we go. Okay. So that going backwards, whatever. Okay. Nice. Okay. Now HCl. So we put it in acid. And will this do anything interesting or exciting in acid?
It could be an addition.
Yeah.
To the alkene.
Yep. Yeah. So it is an addition. So there we go. And specifically, it'll be a Markovnikov addition, meaning that the interesting part goes on the more substituted or more stable part. In this case, that the benzylic position is going to be more stable. So we're going to put our chlorine there. Okay. And now add magnesium, and we add CO2 and then hydrogen, or put it in acid. Okay. So here we're making a Grignard. Okay. With the CO2, we're carboxylating. And then the H plus is just turning it into a carboxylic acid. Okay. So maybe I have a whole bunch of space over here, so maybe let me draw it out nice and big. Okay. So where that Cl was, we make a Grignard and then we add a CO2. So there we go. We've added that onto there. Okay. Diazomethane, which we've already seen today again, and it's a very nice structure to work with. Let me just draw an arrow to make sure it's there. Okay. So diazomethane now. So we're going to go from an acid to a methyl ester. Okay. Nice. So, okay, then that's good. All right, and then we could use this hot concentrated potassium permanganate, and all right, we can do that. Right, we just lose and destroy all of the work that we've done, but hey, it's an option, right? And then you can heat it and lose an H2O in some sort of, let's see, condensation, right? All right, well, let's not worry about that right now. We'll go back. All right, now we have methyl magnesium bromide, and we're adding it to over here. Okay, so we're adding a Grignard to an ester. So we're gonna pop the ester off and replace it with whatever's on the Grignard. So it looks like that. Okay, and let's see. Oh, this becomes an alcohol. Yeah. We're adding two equivalents. Yeah, it does. So it becomes an OH and has two of these guys hanging off. Okay. And now we add sulfuric acid. So we wind up with this thing over here. Okay. and we're able to check against what we've got, what we've what we've worked our way towards, and it makes sense that this is what we get if we heated it with sulfuric acid. Right. Now, finally, we do ozonolysis. So here's this double bond. We can break it with ozonolysis, and okay. So instead of that double bond on each side, we just replace it with a ketone. Okay. Going back up to here. So we did this over here with the hot concentrated potassium permanganate, so we got up to here, right? And then you heat two carboxylic acids in the presence of each other. Does anybody know what that'll get you? Oh, okay. Yeah, I'll tell you. This is not much of one that we've seen a lot either. So you wind up making an anhydride like that, right? And now you have an alcohol. Okay. So this alcohol is a pretty reasonable nucleophile. So it'll go and kick these things off. And all right, so we'll get an acid up here, and then down here we get an ester with what we're working with, right? Diazomethane, so we know that there's an acid, and here we go, right? Make a methyl ester instead of where that acid is. There we go. All right. Yeah. So that will cover it. These are like totally separate things here. This whole roadmap thing is like super disorganized. So there we go. Okay. Yeah, it includes a few like reactions that we haven't talked very much about. So whenever we see those, I'll just try to get past that. Okay. Any questions?
Wait, does the diazomethane only react with the acid?
Yes.
Okay.
Yeah, it specifically reacts with the acid. Reason being is that it has to pull off that hydrogen in order to become a CH3N2. And at that point, that N2 is like a great leaving group, so it'll come right off. But if it's not an acid, then it won't have anywhere to pull that hydrogen off of. All right. Anything else? I'll open up C. Okay. Oops, let me save this one too. Okay. Here we go. So we have this thing that we start with. All right. We're starting with this thing, and then we're adding something to it, and oh wow, look at this. This is we're really not given any information here, huh? All right. Let's work backwards. We're going to start from something else. So how about we work from maybe from what's over here. Okay. So let's start from over here and we add two equivalents of base. Okay. So here's two equivalents of acid and two equivalents of base. So, all right. Not too interesting. And then you add some acid chloride and okay, cool. So it makes anhydride, which seems good. Yeah, okay. From there, let's see, what direction can we go? Okay, we can add sodium, SOCl2. Okay, to this thing, so we will get two acid chlorides on either end. All right, and we can add lithium aluminum tritert butoxyhydride or tritert or whatever oxyhydride. Okay, two equivalents, and this turns these acid chlorides into, does anybody remember what it does?
Aldehydes.
Yeah, there we go. Okay, so here it's two aldehydes. Okay, oh, and it just goes back over to here. All right, cool. So we're going to have to go this way now. So here we have these two amides. Okay. And we add a halogen